Alright, chemistry class, let's talk a little bit about galvanic cells. In the other video we looked at balancing redox reactions, and those are the types of reactions that are happening in batteries, in galvanic cells, also called voltaic cells. So we're going to spend a little time here going through this worksheet and talking about what you need to know concerning a galvanic cell. Okay? In this one, we are going to be also balancing redox reactions. They may be simple ones, but then we're going to then let that redox reactions tell us about the galvanic cell, how it's structured, how it's set up, and tell us a little bit about maybe what's occurring in that galvanic cell. So let's look at number one together. You are given this reaction. This is the redox reaction that is occurring in a galvanic cell. And we're going to assign oxidation numbers, because right down here it says list the species being oxidized, list the ones that are being reduced. The only way you can find that out is by assigning oxidation numbers. So an element all by itself is 0. Here this iodide ion has a charge on it of -1, so each of these are going to be oxidation number of -1. Here the F, that's a fluoride ion, also -1. And here the I2, 0. So what's happening here is this F atom, there are two of them, the oxidation number is going from 0 to -1. So they are being reduced. This is your reduction right here. F2 is being reduced. Here, the iodide ion is going from -1, each of them, to a 0. It's going up, so it's actually being oxidized. So the iodide ion, the I negative, is being oxidized. Okay? So what we want to do next is we want to look at the E cell of this, and I will always give you the standard reduction potential table that would be required in order for you to look up these values. Okay, so I have mine here. Let's look at calculating the E cell for this. Let's write the two half reactions of what's going on. This is F2 turning into F negative. This is that was the reduction, right? So F2 and 2F negative. Over here, the oxidation was 2I negative producing I2. But what we're really interested in is right now is, remember, there's a tug of war. The ions are fighting over electrons. So we're looking at comparing iodide ion and fluoride ion, or the F2, the I2. Those two elements are fighting over the electrons. So you're going to look on the standard reduction table and try to find the reduction formula for those two. Now reduction is going to look something like this. In this case, the F2 turning into F negative, or the I2 turning into I negative. And I know the I is not being reduced, but that's all that's going to be provided on the table. So we look at the table, and when I look in the table, I find, here it is, F2. On the table it says F2 picking up 2 electrons turning into 2F negative, and then it gives you a value, 2.87. That's the relative pull that F has on electrons. And then we look for the reduction of I2, which is further down on the chart, and it's listed like this: I2 plus 2 electrons producing 2I negative. Now this right here is not happening in our reaction. That's because you'll notice this has a lower value. The value of this is 0.53. So this is going to lose the tug of war. This one's going to win. F2 is going to win the tug of war. That means I, because it has a smaller pull on electrons, is not going to be reduced. It is going to be oxidized, which is what we wrote up here. It actually is going to lose those 2 electrons. This is the reaction that's going to happen with the iodide, whereas this is the reaction that's going to happen with the fluorine. Now we just take those two values, and to calculate, you always take the bigger number minus the smaller number. Okay, it's always the reduction value minus the oxidation number, or the cathode minus the anode, but it's always just bigger minus smaller. That's all it is. So 2.87 minus 0.53 and that's going to give you your voltage, or the standard reduction potential of that galvanic cell. So it says what species receives electrons from the anode. So who's receiving electrons? That's going to be your F2. Okay. Who's donating them? Well, that's going to be the I negative. Okay. So you just have to remember that reduction is gaining and oxidation is losing. All right, let's look at the next one here. The next one. Actually, what I'm going to ask you to do is, why don't you do number 2 right now? You can pause the video, do number 2. You're given the half reactions right there. All right, you're given the E for both of them. Now, what you're given is you're given reduction reactions for both of them. But one of these is one of them is going to be reduction. The other's got to be oxidation. They're giving you both reduction. The bigger number is going to be the one that is going to be reduced. The smaller number is going to be the one that is going to be oxidized. So this half reaction is actually occurring, but this one here is not going to occur because it's going to lose the pole. It's pulling with a smaller force than the Ce plus 4. So the actual reaction that's going to happen with the cobalt is going to be the reverse of that. That should be a small o, sorry. That's CO. There we go. This is going to be your oxidation that's going to occur. This is the reduction that's going to occur. To find the E cell, you always take big number minus small number. Okay? You can try the rest of these here and see what you come up with. Okay, let's look at number 3 together. In number 3, it says there's a voltaic cell, and they only give you line notation. Well, if you've got line notation, you know everything you need to know about that galvanic cell. So what's happening here is the Al is turning into Al3+. This is always going to be, when it's written like this is always the anode. This is where oxidation is occurring on this half, and this is going to be your cathode. This is going to be the reduction half. So you could easily write half reactions just by looking at the line notation. It's just like this. Al turning into Al3+ by losing 3 electrons. Over here, Pb2+ gains 2 electrons and turns into Pb. Now, how do I know it's 2? Because plus 2 has got to go to 0. So it's got to be 2 electrons there. Here, the Al turned into 3+, so it gave up 3 electrons. Now, if I want to continue this properly and really balance this, I can't have 3 lost and 2 gained. So I'd have to multiply everything here by 2. And everything here on the other one by 3. Okay? So this way, what really is happening are these two half reactions. And 6 electrons are lost, 6 are gained. Okay? But in any case, I would calculate the E cell. What would I need to do? I look on the table that I provide everybody, and I look for the battle between these two ions, the Al and the Pb2+. So here is Pb2+ picking up 2 electrons. That standard reduction is negative 0.13. The Al there it is. Al3+ picking up 3 electrons. That is negative 1.66. So, even though they're both negative, you're always going to take the bigger minus the smaller. Okay? That value is going to give you the E cell of this. Now, if the E cell is negative, then that means actually that the battery will not work the way that we arranged it. If the E cell is positive, then the electrons will flow. Alright, the balanced overall redox, well, I kind of already did most of the work here. I just want to bring these two equations together now. So it's going to be, remember, you never have electrons in your final reaction, so it's just going to be the 2Al reactant here plus the 3Pb, 2 plus, turning into 2Al 3 plus and the 3Pb. Okay? Alright, you try. Actually, I'm going to do 4A with you, and then you can try to do 4B. Okay, so 4A, assign oxidation numbers. We are trying to find the E cell for this reaction. So let's assign oxidation numbers. 0, 0, plus 1 for each, negative 1 for each. H is going from 0 to plus 1. It's being oxidized. I is going from 0 to negative 1. It's being reduced. So oxidation and reduction. The oxidation is the one that's going up, so that's going to be H plus, like that, and 2 electrons. I2 is being reduced. By gaining 2 electrons. Okay? But really they're not even asking for all of this. I just did that extra. They're looking for the E cell. And so we look at the 2 ions. Look on your chart and see which ion is going to win the tug of war. Well, I've already told you who's going to win the tug of war, because I identified it by assigning oxidation numbers. The I negative here, the I2 is going to win the tug of war compared with the H over here. It's going to gain the 2 electrons. H is going to give up the 2 electrons. So even before I look at the chart, I probably know that the I2 is going to have the higher E value, the higher standard reduction potential. But let's just verify here. The I is going to have, over here if I look on the chart, it is 0.53 compared to the H plus. Remember, H plus, everything is compared to H plus, so H plus is going to have a value of 0. Okay? So I just take big minus small, and you've got your E cell, the voltage for this battery. Okay? You try B. Pause the video and try B. Alright, the last problem that I am going to do for you, because I'm going to leave 6 for you. You're going to do number 6. I'm going to do number 5 for you. It says for the following voltaic cell, and again they just give you the line notation, and we're going to do all of these things. This really incorporates everything that we've talked about. So this is kind of a great review problem for everybody to work through. Okay? So number 5. Here's what you're going to do. You're given the line notation for this particular galvanic cell or voltaic cell, and we're going to first of all draw a picture of the cell. So your 2 metal electrodes are given to us. The ions that are in solution are given to us. That's just the concentration. And the double vertical line means that's the dividing, the porous barrier or the salt bridge, either one. So if I was to draw it the way they're asking, okay, remember we can have a salt bridge or we can have a porous barrier, it doesn't matter. So we're going to have a solution over here. We're going to have a metal electrode. We're going to have a metal electrode here, and we're going to connect it with a wire. We're always going to put our anode on this side. We're always going to put our cathode over here. This is where we're going to have oxidation. This is where we're going to have reduction. Electrons are going to flow from anode to cathode. So on this side, we're going to have our Fe in Fe2 plus solution. The other side, we're going to have our Cu in a Cu solution here, 2 plus. And the salt bridge is going to have, I don't know what it's going to have, because it has to have plus and negative ions in here, okay? We're not told exactly what they are. We don't care. They could be Na and Cl or whatever. But remember that iron ions are going to be created on this side more and more. You're going to have a buildup of plus over here. So that means the negative ions from the salt bridge are going to be flowing into this side to keep the left side neutral. And then you're going to be losing positives here, so the positive ions from the salt bridge are going to be flowing this direction. Okay? Write the cell half reactions. Now the cell half reactions are going to be here. Over here you've got iron that is losing 2 electrons and turning into iron ion. And here you've got the copper ion picking up 2 electrons, turning into copper metal. Alright, we already labeled them. This is your oxidation, this is your reduction. We have those already figured out. So we did B and C. Label the direction of electron flow, we already did that. And label one, this is cathode and anode, we already did that. Write the overall cell reaction. So if we do this, we're just going to bring these two together. We already have 2 lost and 2 gained, so that's already good. And we're going to have Fe, reactant, along with the copper ion, producing Fe2 plus and copper metal. If we were to calculate the voltage for this, we look up on our table, which I always provide for you, and I'm looking for the battle between Fe2 plus and Cu2 plus. Who's going to win that? So I look at, we already know, I already know who's going to win. The electrons are flowing from anode to cathode, so we already know the copper is going to win. But I just want the values. I want the values of their pull force. So I look at this, and I've got on my chart, I look for Fe2 plus. Down the chart a little bit here, it is a value of 0.44, actually negative 0.44. Copper 2 plus is further up the chart, and it is 0.34. So you just have to calculate to get the E cell here. You would take larger number minus smaller number. Doesn't matter if the smaller number is negative, doesn't matter if they're all negative. Always bigger minus smaller. This calculation is going to give you the voltage for that cell. Okay? A positive voltage, when this number is positive right here, it means electrons will flow. If this voltage is negative, it means it's not going to flow in the direction that we anticipate because we've got it set up backwards. Okay? Alright, you try number 6, and then make sure that you check with your neighbors or ask me any questions that you have.